Okay, today we are going to see the different kinds of controls, and we are going to study what is called proportional control, what is called derivative control, what is called integral control. But before we do that, we need to put the framework of all the components that a control system has. So let's begin there. And here we have a division, you may say, of disappear from there. We have control systems of two kinds of control systems. One, some are called closed loop, and others are called open loop systems. Okay. For example, if you turn the light switch on a lamp, that's an open loop control because it's just the on or it is off. The closed loop actually measures something, compares to what you want to do, and then takes action. Typical case, the cruise control in your car. You set it to go 65 miles an hour. The sensor sends whether you're going faster or slower, and depending on whether you go faster or slower, the car goes faster or goes slower until it actually rides at 65 miles an hour. So in here we're going to look at the objective is to use the computer to design the systems. In this case, we're going to be using MATLAB and Simulink. And if we are going to build real systems in 3 dimensions using controls, we'll be using SolidWorks and SimWise 4D. So the definition is, of course, a system to regulate uh, in some way that you want. Closed loop system, as I said, is the one that measures and then takes an action. Open loop does not use feedback, adjusts the flow of energy according to some rules. Yeah. Automatic control is the one that acts without intervention, or just we found this even in unmanned vehicles or UAVs, all that stuff that make decisions based on situation. And of course, we use computer models to be able to do this because it's much cheaper, better that you build something on the computer as opposed to um, spending lots, thousands of dollars to do it on the shop. Now here's a very important slide. This one is giving you the overview completely of what a control system could have. The block that we have in here, this is the one that um, this is your system here. This is the plant itself. Let me see if we do this. This is in here. This is the plant. See there. This is your system itself. What you want to control, and the output obviously is the one we're going to measure. So this is your feedback control. See, let's write it down. This feedback here. All right. So in the class where we study just modeling and simulation mechatronic systems, like we studied mainly this. But now we're going to study all these other blocks. Now let me explain each one of them. First of all, when you are starting here, you start by setting up a reference or a desired value of something you want to control. This is this reference R of S in here. The feedback, the measurement of your system comes in here. Usually this is like in RPMs if it is a velocity control system. But this H of S this box transforms the RPMs into a voltage. And this one is the also a voltage here. So voltage with voltage, then you get a difference. That's what this E is called the error. Let's write it down. The error there. And so depending on what the error is, you need to do the correction. So in here you can see this could be the dial on the thermostat, if it is a thermostat, or in the you know, some number that you set the measure what you want. This transforms it into a voltage. So these two voltages get compared, and the difference is called the error. The error, you know, this it can be used depending on what the controller is. Some logic, control logic element, whether this gives a command to a motor, perhaps. This is your actual control, this guy. This is your control. This is the one that is going to modify your system. So you see this G sub M is the one that we call it final control in our little thing here. See? So in here, this is the one that control your system. And then you may say, Professor, what is this whole thing in here? Makes it look complicated here. Well, you know, we need to be ready for the unexpected. Yeah, you have a measure here, you have gone through here, and then the controller system say, oh, you know, your system is going to be modified a certain way. But all of a sudden, there is an external agent. Like in the case of a, let's say if you're trying to keep the temperature of this room at a certain temperature, and somebody opens the door, well, this is the external disturbance. So this is, that's the word we use with this disturbance. Okay, so in here you'll see this is called disturbance elements. So you have a list of all the things if we for you to remember. Basically, I would like this slide be engraved in your mind. Because if you do this, then you will know which block you're dealing with. I am not saying all control systems have these blocks. That's not what I'm saying. But this is basically all possible. Okay? So some of them may not have this one, and likely also not this one. And so we'll start over here and directly with the control. And some may not have the disturbance. So I think this is a complete picture, you may say, of what possible you could have. So our focus is going to be here on this value here, because this is the one, this is the heart of the control system. This is the one that, based on the error that we have, is going to take action. So this is the one that can be proportional control, derivative control, integral control, PID controlled, all that stuff. Now, you realize that each one of these blocks in themselves, they are expressed in a block diagram with an input and an output relative to each. So you could say, for the control system, you know, the input here is this, not the input of the system, but the input to the controller. And then the output is going to be, but this output is the input to this one. And then the feedback from here, this is the input to this block. This is the output of this block. But you see, everything gets assembled together. So let's go on. The control loss you have some of the response that you would have first uh, to an input. The system would settle down until it will reach what we call a steady state error, would be the error that the system will have. Let's say if the input is up here and the response didn't get all there, then there is some error that will always exist. Some of these control systems get rid of this error but cause other problems. Like then you might get rid of the error, but you could have a system that oscillates too much. And for example, in a cruise control, you don't want the the system oscillating. You know, your car will be jerky. It's gotta be smooth. Maybe we accept the steady state error of, let's say, 1 mile, and we adjust the dial on the needle that marks the velocity or the logic that tells us what we're doing. So, what the car velocity is. So, you know, there's ways to get around that. The objective, obviously, is to minimize the steady state error, to minimize the settling time, and to achieve other specifications that the control system may give us or might have. So these are the different kinds of controls. You have something that we call the two-position control, which is on and off, like an on and off switch, or they are also called bang controller. There is something called proportional control, and then there is a control system usually used for first order systems or for second order systems. Remember what is the order of a system here? You see that we talk and speak properly here. The order of a system is the degree or the, the power of the highest derivative. Like if you have the first order derivative, then it's called first order system. But if you have s squared and the transfer function, then you have second order systems and so on. And in here you have the integral control, and then you have derivative control. Now let's talk a little bit about the two-position control system. Always there is some neutral zone between what the system is going to do and the action. Like for example, if you set up the thermostat in this room to 72 degrees, you have the measure of the temperature in a thermometer that, depending on how the system is built, it may require to go just a little bit over 72, small amount, and then it turns the air conditioning on. And then you lower it and it will go a little bit below 72, and then we'll switch off, producing this kind of neutral zone and turning it on and off. Okay, so here you can see that the error in here is the R minus C, which is the control variable in here. Then you have this on and off controller. This is an interesting one because it's a hydraulic system that is a liquid level control. So this floater here is supposed to be on a certain level here. So this is your fluid here. Yeah, you can have it in here. Water in there. If it gets to a certain level, you could activate this switch here. See, and then depending on what you do here, either you disconnect by having this actuator here that open and closes this valve. So if this goes down, and then depending on how it goes down, this would open up, and if this goes up, then this would shut off the valve. That's the idea here. So how does it work? You have, let's say, like the filling curve in here, and then when it gets to the to the switching gap, as I say, it goes a little bit above that, then it will empty it and depend. So this is the overshoot, and then it will be the undershoot, and then it go back again and does again this cycle. So this is the liquid level control with the on and off controller. Yeah, this is the okay, let's go here. This is called bang bang controller. This is the control system where you would go either on or off, but on this would be the function that represents your control system. But in real life, you can go, you don't go on and off. There is always a dead zone in there, so it produces this kind of curve. Now let's go something more practical and perhaps a little more attractive for you. Here you are cooking your turkey for Thanksgiving, and you have this system. This is what you have. Here's an oven in here. This is your oven. And there's your turkey there. And you have a sensor that measures the temperature. And in here you see you have, it's called potentiometer because the, here you set it up to, let's see the experts. Turkey, how many degrees we put to cook? You don't know this one. Not 400, between 350 is about normal in there. But for how many hours?
Number of minutes per pound.
There you go. Depends on how big. He knows. Huh? But I usually do it for 3.5 hours, and I have had a wonderful experience. All right. So here we go. We have this here. Set the temperature. So this little box in here is going to sense the voltage that comes from the thermocouple that measures the temperature. And inside this box is going to say to the control system in here, hey, turn the element on or turn it off. You reach 350 degrees or not, and what is the situation? 350, and then turn it off to try to maintain this. But you see, there are several things that work against you here, and that is that you lose heat. See, you lose heat this way. If we can represent it this way, like this. By the walls, you lose heat. And that is your disturbance. And once this gets down, then this thing goes back again. So this is what you see, and the oven here. Actually, I'm gonna take advantage of this slide because here's your system. You see, here's your oven, and this is the output. In this case, the temperature here. As you can see, and here you will have a measure that goes back like this. Yeah. So this is your aging here, this measure here. And what's happening is inside that box, you have a measure here, so that for the set time, what did I just do? And then here there will be a control to your system here, and this is your how do we call this? Let's call it G. Yeah. See, so that relates your physical system to our little block diagram. So once again, this is our system here, and the way we want our system is either a state space form that contains all the equations and the inputs and outputs, or we wanted a transfer function, or it could be expressed in a MATLAB function. But that's your system that contains the differential equations, contains everything. So this system also is going to have that. So this is the in here you have the voltage from the potentiometer, which would be this one over here. K2 times T2 is the voltage from the temperature sensor. So this is the temperature. This is where this K2 comes from here. And this K sub A would be the one on the amplifier, meaning this one right here. Okay? So this way I tell you how you actually implement the control system. Now, because we are engineers and we like equations, so here they are in more detail. So whether you use bond graph models or you use any other one, in here you have this. This is your equation for the system. This is the physical system equation, derived any way you see fit. In this case, you know, the system, you could see, has only one differential equation, and but this is what controls the system. Now you would like T2 constant, so we will have to establish the Q that you get from the heater minus whatever it gets lost, and you will have this Q steady state, which would be this this is the control condition, you may say, and the circuit that is going to take action, and the heater output is here, and then we establish a control law. See, this is important. I think I'll emphasize this word. Control law means what type of controller are you going to put. So look what it says in here. Make the rate M of controls. What does it mean? What's the word for that corresponds to this symbol? Proportional, right? Okay. So we make the control proportional to the difference in voltages here. So this is called proportional control, obviously, because the more error that we have, the more correction that we make, or the less correction that we make. So that is called proportional control, and so that's then we express it in this function like this. Very good. In this case, you have that the temperature is T2 minus 200 would be what the error is. This would be the other one would be T0 minus 70, which is the outside temperature. And then this is again the equation, and then you will have to implement these differences into the equation. But this is the block, okay? The block of this system for the oven. So here's your oven, okay? And it has this kind of transfer function. Now this one is we have done several transfer functions and gotten the root locus plot and the response and everything. This is a very simple one, right? First order system. And here you have the measure here, you can see. And it feeds back to our set point. Calculates the error, just to emphasize, so that we do it over and over. This is your error. And this is your correction. This is your control right here. And what is this now here in the case of our turkey here? What is this? So somebody opens the door, right? Just like me sometimes say, oh, is it ready? I mean, there's then the whole system gets disarray, right? Because you introduce yourself an error, and you are affecting the controller in here. So this is your, you could put it external disturbance. Wow, very good. So let's see. Important parameters that we need. We need to make we need to look at the time constant, the damping ratio, and the natural frequency. These are the things, these are the important things that we need to study. The stability of the system, speed of response, speed accuracy, or something like that. But all this comes after we have all our block diagrams in place, right? When we are in Simulink with this is where we say, oh, the time constant is too small or too big, or the damping ratio is this or that. Perhaps one thing that about the natural frequency, we briefly mentioned that remember the characteristic equation is the denominator of the transfer function, right? The roots of that equations are the natural frequencies of your system. Okay. Now here we have a electromechanical position control system. This one now is a second order system. Now you see here is a, how can I say, this is like what I would call a word block diagram, and this is our block diagram of the system. So basically we are practicing what I told you at the beginning, a system that has all the components to a system that has some components and not others. But in this case, what do you have? This is the system here. You can see, look, this is your system. Again, once again. And then you have, this measures the speed, and what happens is feedback potentiometer, meaning from this RPM, you know, the omega that you have in here, right there, this omega, this is going to be converted into some voltage in here to make sense with, to compare here. So in here you have this comparison of the voltages and gets transformed into a command to the DC motor, you see. Yeah, So this is your again, I would put here your controller, huh? Now your control system, do you realize is in fact another system, huh? It's another, because what you're doing is you have your physical system and you're adding to that system this controller, which together makes another system. Because you know, not together, this one and this whole thing operates together like this. Yeah. So here you have now in the way when we use the notation here of the block diagrams, here again your system here. You can see second order system here. Okay. You have your feedback. This is the potentiometer here. This is the command potentiometer, meaning this is your dial setting, transforms into a voltage, and this is of course right here your error in there, and then whether this gets amplified or conditioned, this signal goes to the motor. This is the command right here. This is the motor itself. This is basically your controller. Yeah. So now little by little, even if you have lots of blocks in front of you, you will be able to recognize which is which, and that's what I would like. Now let's take a peek at the first type of control. This is called proportional control. This is the characteristic of the proportional control. The feedback signal is proportional. Yeah, it's proportional to the error. Proportional to the error. So what does it mean? The more error, the more control. The less error, less control. That's what this means. So this control system is it's pretty good. You know, it's fast, but it has other problems. We'll see it. So the more error, the more the control. The control signal, you see, this is proportional here, proportional to the set point and the current value, meaning the measurement. Yeah. So there you have. This is the system, their system here, and you measure the velocity control, and then in here you do the comparison. So this is your set point, your set value. This is the way you want it, and then it goes to this power amplifier, and this the control system here. I mean and the system, of course. Here the proportional control, we are going to see in here the equations of the system. You have these two equations here for the system, and this is the control law. So it's the control, the proportional control in here. So these are the equations of the system plus the equations of the control. Yeah? And then in here, if you have, this is in case, let's say, we consider a disturbance torque in this case, what do you have? You have your system here, you measure it, this is the tachometer, and this is your proportional control in here. These are the transfer functions that you can have, because now you realize that this one is an input here to the system. This is your input. But isn't it true that this guy, this disturbance here, this is also an input to the system? I'm going to call input disturbance, yeah. When you obtain the transfer function, remember it relates one output to one input. So this relates the output, the output, this omega of s like this, in relationship to the input over here, to this one, to the input torque in this case, I guess, omega t like this. But this one is the output, again the output, omega of s, in relationship to the disturbance, which is your let's call it t of the disturbance of s, like this. Now it would make sense, it makes more sense, physical sense, what I have been telling you about the transfer function matrices. Each one of the components of a matrix is one input with respect to, it's one output with respect to each input. So this is the way we have it here. So in here you will have the way you have the transfer function. You say a change in the desired speed can be simulated by a step input, which you put it in here, and then this would be the final value once you calculate the whole thing. Of course, these are things that I don't want you to do it by hand. We'll just use MATLAB and simulate. So in this case, you have the change in the torque modulus unit step function, and then you will have the to calculate what the final value is. Summary of proportional control. First of all, for the first order system, the output never reaches the desired value. So this you have to know. When you use proportional control, this will have always an error. You will never be able to get rid of this unless you do something else. So the output never reaches the value if resistance is present. So although it can be made arbitrarily close by choosing the K gain to large to offset the error. The output approaches its final value without oscillation, which is good. In other words, it's a smooth control. The time to reach this value is inversely proportional to K. So the more control, the faster it gets there. But the output due to the disturbance at the steady state is inversely proportional to the gain. And you can say this error is present even in the absence of resistance. So proportional control is good, but it has its drawbacks. Yeah. So I think this is the you may say the introduction to all these type of control systems that we have, and we'll make another video with the other kinds of control. So I'm going to stop this one now.